Hello and welcome back to the video guys. So in this video we'll cover assignment on principal component analysis. But before starting our assignment, I will quickly demonstrate the steps involved in PCA. These are the same steps that we have learned in our previous video where we had covered the theory on PCA. Now this is just to give you an idea about the working of PCA. And we have functions for doing all this in R, so we will not be doing it manually anyways. Now for doing these steps, we will be using iris dataset. So first we will call the library datasets and then we will load the data using the data function. After this we will exclude column 5 from it and store it in the variable df. Now in step 1 we will center and scale the data. So for doing this we will use scale function. But if you recall, earlier we did scaling using sapply function, where we made a customized function for min-max scaling. However, there is already an inbuilt function in R that you can use for scaling. So we can give the data as the first argument and then mention center is equal to true and then scale is equal to true. Now what is centering? Basically in centering, you are changing the values but not the scale. So a predictor that is centered around say mean means that the entire scale has shifted towards mean. In short, if you have centered the variable, you can still interpret the coefficients the same way because 1 unit of a centered variable still means 1 unit. But when you use scaling, then variables are measured on a different scale altogether. So you cannot interpret the results directly. For interpreting the results, first you have to descale it and then only you can interpret them. So we will move ahead and do scaling and store it in the variable df.scaled. Then we'll move to step 2, which says compute the covariance matrix. Recall the second step of PCA is to compute the covariance matrix. We can also use correlation matrix here. Recall correlation measures the strength and direction and covariance measures only the direction of the relationship between the variables. However, we are creating covariance matrix only. So we can use the COV function and give our scale data and then round the values to second place of decimal. Then we'll move to step 3, wherein we will calculate the eigenvectors and eigenvalues. So for this we can use eigen function and give our correlation matrix as the argument to calculate eigenvectors and eigenvalues. We will store it in the variable res.eig. So if you print this variable, you can see in the output that eigenvectors and eigenvalues have been calculated. Then we'll move to step 4, which says compute new matrix by transposing eigenvectors and then multiplying it by transpose scaled data. So we can use t function to transpose the eigenvectors. Now eigenvectors are stored in res.eig variable. So we can subset the eigenvector from res.eig variable using the dollar function and then store it in the variable ev.t. Similarly, we can transpose our data and store it in the variable df.scale.t. After transposing, we will multiply the eigenvectors and our transpose data and store it in the variable df.new. Now if you see, we are using the pipe operator for our multiplication, because if you want to multiply a vector or matrix, you can do it by using the pipe operators. Now in the last step, we will transpose the new matrix again. Basically it is back transposing it. And then assign the column names as PC1, 2, 3 and 4. Now we can use the head function to print the first PC values. So as you can see, the principal components are printed here. So that is how we create the principal components manually. Now we'll go to our assignment and perform PCA on a different data. Also in the assignment, we will use prcomp function, which gives us result directly, and all these steps can be skipped. So let's read the overview of the problem which is given here. It says, as a business analyst at a large global asset management firm such as Vanguard, JP Morgan, Morgan Stanley, Fidelity, etc., the portfolio management team has asked us to help them build a risk model for the Dow Jones Industrial Average. Now, the Dow Jones Industrial Average is a basket of 30 large publicly traded stocks. As business analysts, we would like to get an idea of common risk between the stocks, and to do this, we will use principal component analysis on their returns. We will be using daily returns on the stock for the year 2012 to 2015. So this was the overview of the problem. Now let's read question 1. So question 1 says, read in the data, make a scatter plot of a subset of columns. For instance, plot data from 2 to 10 column and report what do you notice. And also explain why would this dataset be a good candidate for doing PCA. So first we will read the data and then store it in the variable PCA_data. After this we can check the structure of the data. I'll not be going into the details. You can pause the screen and you can check the structure. Similarly, we can check the summary, but I'm skipping it again. After this, we will exclude the first column as the first column has dates. So we can exclude column 1 as shown here. Then we can use the plot function to plot our scatter plot for the first 10 columns. Now I have given the explanation of scatter plot. You can pause the screen and read through it. However, same rule of interpretation of scatter plots that we had discussed in our earlier video of discriminant analysis will be applied here as well. And if you haven't watched the video yet, then you can go to the video and understand these rules of interpretation for scatter plot. So moving to the first point that says, most of the data seems to have a positive linear relationship except few variables such as BA versus CAT, CVX, CSCO, etc. The next point says that data seems highly correlated and there are 30 variables under observation. So dimensional reduction would be a good idea so that lesser variables can be worked upon to achieve a parsimonious model. Also, PCA would help us to address the issues of multicollinearity. Hence, we can conclude that PCA is a good choice for this problem. Now that we know PCA is required, so the next step would be to scale the values and check if the variables look normal. So we can make a histogram of few of the columns and then we will report our observations. So we can use scale function to scale the data and then store it in the variable PCA_data_scaled. After scaling the data, we will proceed to creating the histogram. So here we will use a for loop for plotting 10 variables. We will use the HIST function and it is a straightforward code. So I will not be explaining it and we already have done it earlier as well. So we can just run it and this will return us the histograms. Now as you can see from the histograms, most of the data is normally distributed with some skewness in few variables. Now we will proceed to question 3. Question 3 says, perform a principal component analysis on the data. Discuss the output, specifically the loadings. So here we can use printcomp function for carrying out the principal component analysis. The first argument here is the data. And the second argument is saying that don't use correlation matrix for calculations. So it will use covariance matrix instead of correlation matrix. That is what we had studied in the theory lecture as well, if you remember. After this, we will run this code and store it in the variable PCA. Then we can check the summary of the output as well. So if you see, a huge summary of the output is printed here. Now in the summary we can see that we have principal components given here. Each component has a standard deviation, proportion of variance, basically how much variance it explains, then cumulative proportion of variance, which means it is cumulatively adding the variance as we go from PC1 to subsequent PCs. So if you see the cumulative variance explained by PCs, 76% is explained by 3 PCs and 82% is explained by 4 PCs and so on. Hence you can see how principal components work. We have 30 variables and just by using 4 principal components we can explain 82% of the variance explained by the 30 variables. That is the whole idea of principal component, that is reduction in dimension. Now we can view loadings as well by subsetting it from the PCA variable using the $sign. So as you can see, again we have got a huge output here. Now the explanation is also given here. So let's read the explanation to understand this output. The first point here says loadings represent partial correlation between the principal component and the variable. The value of this will always lie between -1 to +1. So you can see here all the loadings are given here. For example, 0.253 is the partial correlation between principal component 1 and the MMM variable and so on. Now the second point says partial correlation measures the strength of a relationship between two variables while controlling for the effect of one or more other variables. For example, you might want to see if there is a correlation between amount of food eaten and blood pressure while controlling for weight or amount of exercise. You can also control more than one variable, but it is not recommended. So when we do this and measure the strength of the relationship between two variables, that is called partial correlation. Also, if you have noticed above, there are some blank values. This simply means these values were very close to 0 and hence R automatically has neglected these values. Then the last point says the higher the loading, the higher is the correlation of that variable with the respective principal component. It basically is giving information about the important variable or contribution of the variable for constructing a principal component. So that is how you interpret the results of loading. Let's go to next question. Next question says, make a scree plot of the model. What does this indicate? And if we are going to use a subset of principal components, how many should we use? And also explain why. So we can use the scree plot function and create a scree plot. Also, I have used parmfro function and given a vector of values 1, 1 because we only need one graph. So we can run the scree plot function and we'll get our output as shown here. Now scree plot gives us the cumulative variance, which I have explained above. Now as you can see, the maximum variance is explained by first few principal components itself. So again, an explanation is given here. Let's see what explanation is saying. First point says, it can be seen from the scree plot that there is a sharp decrease in the variance till principal component 3. Beyond it, the graph starts to flatten. And after 4th PC, it is constant and a marginal drop or no drop in variance can be observed. Therefore, 3 or 4 PCs can be taken as a number of PCs of our choice. Furthermore, to decide whether to choose 3 or 4 PCs, we will have to employ other approaches such as eigenvalue approach, communality method, or priori variance threshold, which is beyond the scope of this work. Then we'll move to next question, which says make a biplot for the first two principal components and explain what do you notice. Now what is a biplot? We will see this in the explanation, but before that let's first plot it. So we can use byplot function and give PCA as the first argument and CEX is equal to 0.5, which means compress the text by 50% to the original. We can run this and the byplot will be printed as shown here. Now as you can see, the graph is very congested and we can improve its appearance to some extent, but let's not get into it at this point. I have given an explanation, so let's read the explanation. First point says the left and the bottom axes are showing normalized principal component scores. The top and right axes are showing the loadings. The points in the byplot represent the scores of the observations on the PCs. The vectors in our case are stocks of the companies and points are the returns. The vectors, that is stock, pointing in the same direction have the same kind of return. Most of the vectors are pointing 1 o'clock to 5 o'clock and the returns vary in this area only. However, if we look at the spread of the data, it is much beyond the area which is covered by a byplot. But since the entire or most of the variability as we saw above in the PCA results is explained by at least 3 to 4 PCs and we have used only 2 PCs based on the below assumption, therefore in our case vectors are spread in one direction only. Now the assumption is that byplot assumes that most of the information can be interpreted from first 2 PCs only. Also looking into another dimension would not yield any comprehensive information. Hence we conclude here. Now the last point says points that are very close to each other in the byplot represent observations with similar values. So that is what we can make out about the principal components from the byplot. Now again, these graphs are only indicative and we can use them to get some insights about the data or the results. And that is the reason I am not very worried about improving the appearance of the graph here. Because whatever insights are required, we are able to get it from this graph only. So there is no point in wasting the time in improving the appearance of the graph. Now let's move on to next question, question 6. It says what are the things the first few principal components may represent? How can we use this model to help the portfolio management team manage their risk? Now let's see the answer given here. First point says to define the approach we will use on 2 PCs and the same can be extended for other PCs. Second point says as there are 30 companies, which means 30 variables, so we will take the top 3 loadings to define our PC. So as you can see, PC1 can be defined as a combination of 3 companies that are MMM, AXP and TRV stocks. Now this finding is based on the first 3 largest loading in PC1. So if we go back to the loading output above, we will find that MMM, AXP and TRV has got the largest loading in PC1. Hence we are using these 3 companies to define PC1. Now in the same manner, we can define PC2 using the 3 largest loading in PC2. So the 3 largest loading in PC2 are for CAT, then Intel Corporation and then MRK. Hence we can use these 3 companies to define PC2. So as you can see here, we have defined PC2 using these 3 companies. Now in the same manner, we can define other PCs as well. Now here is a remark given here. So let's read the remark. It says if we look at the PCs, all the values of loadings are very close and we can't really differentiate among different variables. This means that most of the variables in PC1 and PC2 are important. However, just to give an approach, I have used top 3 loadings. But in this scenario, the recommendation is to conduct factor analysis to get the factor loadings, which would make the task easier to identify the variable contribution in the PCs. Now, factor analysis is a different topic altogether, and we cannot go into the details of it at this point. However, we can use the above methods that also works fine to a great extent. Now, the next point says insight for the portfolio management team. It says since principal components are ordered in ascending order based on the variance explained, hence we can use the principal components to identify the potential companies that has yielded a good return based on S&P Dow Jones Index. We can consider up to 3 to 4 pieces, as majority of variance is defined by 3 to 4 pieces in our case, and within those pieces identify the potential companies as we have done above. This will give us the companies that have yielded good returns. So just like we have made a criteria to define principal component 1 and 2 based on few companies, we can do it for the rest of the PCs as well, and this will indicate that these companies have yielded good returns. So that is the insight we can share with the portfolio management team. And with this, we have concluded this assignment, guys. In this assignment, we have learned to implement principal component analysis. We have interpreted the output of PCA. We have interpreted the loadings and also learned about biplots and its interpretation. In the beginning, we also saw the steps which are involved in principal component analysis. Those steps were not required. I have just demonstrated it to make you understand the process. Then in the end, we have concluded our findings and made recommendations to the portfolio management team. So that will be all from this video, guys. Now I'll see you again in the next video. Until then, see you.